Hello, my name is Nisarg Shah, and this presentation is on a project I did on nutrition facts detection from a food item wrapper. So here is a very general overview on what we're going to see today. We're going to start with the algorithm overview. There are some parts of the algorithm which I'm going to explain in detail, which are enhancing the image, removing the outer regions, aligning the image, segmentation, some challenges that I faced during this project, application of the project, acknowledgement, and references. So this algorithm is basically gonna cover a few parts which I've divided them into. First is to enhance the image, is to irrespective of the image quality, we need to be able to go for the further processing. We're gonna remove the outer areas, align the image irrespective of the misalignments it may have. Prepare a segmentation mask, which we're gonna eventually apply the mask onto the original image and segment out the parts, and those parts desirably are the nutrition facts in the table. Okay, so why do we need to enhance the image? So the reason why I need to enhance the image is the user this application that I'm gonna explain in the coming slides is may have the user taking the image from a mobile camera, and as you know, mobile cameras may not be the steadiest camera, and the conditions may not be the most supportive one, so there can be lighting and alignment or blurring problems. So irrespective of the image quality, as I said earlier, we need the image to be eligible or good enough quality for the further processing. So we need to enhance the image and get it to a standardized form. So how do we enhance the image? So for that, we have taken three different filterings and multiplication techniques for this. So first I do a 3x3 median filtering. 3x3 median filtering basically gets rid of all the standard noise, and it also smoothens the image. Now, as I said earlier, there can be a lot of lighting problems in the image. When I talk about the lighting problems, I talk about some really bright or some really dark areas in the images which are difficult to read from. So in order to get rid of that, we need to balance out the histogram of the intensities. So, which basically, if we do the histogram calculation, it will remove all the sharpness, and give proper lighting distribution across the whole image. And since for the further processing we need a binarized image, we do adaptive thresholding on 16 cross-section kernels, and we set those areas set those areas where the intensity variation is less than zero point 0.3 to dark, and more than that we set it to white. So here is the first checkpoint after the enhancement stage. This is what the output that we have. So our image now is basically a binary image, and as you can see quite clearly that all the nutrition facts are quite clearly highlighted. So we are going on the right path. So removing outer regions. So as we discussed earlier, now that we have a noise-free image, and now we have image which is worthy for the processing towards creating the mask, we need to remove the outer areas. So by outer areas, I mean the areas out or areas which are excluding the nutrition fact table in the image. So now we need to get rid of all those white items that were there in the background in the last image. So we need to get rid of them. So we take as our reference, which we want to keep in the image, is those horizontal lines, the black lines that are always there below the image. We keep that below the nutrition facts. We keep them as our reference. So whenever we will try and detect those lines, and whenever we have those horizontal lines which are always underlining the nutrition facts, we will try and keep preserve those, and we'll try and get rid of all other outer regions. Alright, so how do we remove the outer regions? So as I said, by outer regions, I mean the information apart from the nutrition fact. Now, if the photograph is taken for the nutrition fact, most area in the image is going to be covered by the nutrition fact, and lesser area is going to be covered by the other surroundings. So when we do a filtering by 200 largest regions, what we get is the 200 largest clusters of the bright regions, where most of them are gonna be the nutrition fact horizontal lines which you want. So they are certainly gonna be in those 200 largest regions. So they will always survive this filter, and rest smaller portions we will get rid of. Then we do eccentricity property application. So by eccentricity, I mean it's the ratio of distance between the foci of the ellipse and its major axis length. Uh, Practically speaking, whenever eccentricity is equal to 1, it means the line segment, and 0 means the circle. So, because we are looking for those horizontal lines, if we do eccentricity property with the value 1, then that means it will only preserve the horizontal lines in the image. But at times there can be possible that, if, as we will see in the demo ahead, that there are chances that sometimes the horizontal lines really don't look horizontal and they look little bit curved. So we keep that value 0.98, and this will preserve all the long and thin regions. By that we mean the horizontal lines that we want to preserve. Then we do the something called orientation filtering. So what orientation filtering does is it only preserves the largest cluster of all the elements which are mostly oriented. Now, because this nutrition table is a table, all the horizontal lines are gonna be oriented to each other because they are part of the same table. So eventually, after we do orientation filtering, we are only gonna see the lines which belong to the nutrition table remaining. Alright, so as you see here, this is exactly what we wanted. We have removed most of the outer regions, especially those three big packets stay in the back, and the label on the back which says $249. Um, Most of the portions remaining are very useful information, but still we have a few more steps to go until we get the perfect mask. So the next task for us is to align the images. This image is only slightly misaligned, but there are many images which are quite heavily misaligned. We need to align them as well. Now this image is also not perfect. There is slightly improved alignment at the end of this step, which you will see ahead. But generally, for those very misaligned images which are generally there, this is the step that will be useful. Alright, now by this step we need to align the image. I already explained why we need to align it. Before we go into aligning, we face some challenges. I faced some challenges before in the previous tab. Two of those were those hanging tiny letters on the bottom of the image. Now to get rid of that, we need to apply the filtering based on matrix. Now what that will do, it will see the whole image row wise and column wise, and those rows and columns where there are very few white dots, it will get rid of them. So wherever on whichever rows we detect those tiny letters, it will consider them as noise and it will get rid of them. So we will get rid of those tiny letters hanging somewhere. Then we do half transform. Half transform basically detects the line and it gives an angle of that line with a horizontal respective line. So by that what we mean is if the image is misaligned, then if it's parallel to the nutrition table's 2D plane, what will happen is the angle at which the nutrition fact horizontal line is aligned, that's the angle where your image is aligned, and that's the same amount of angle which you want to revert back in the opposite direction and get the image properly aligned. So to do that, you apply half transform. It will see those horizontal lines on the nutrition fact table. It will tell you the angle at which they detected, and if you apply the negative of that angle on this particular image, it will be perfectly aligned image. Also, if you notice, the some of the lines were discontinuous, some of them were broken, unconnected portions. We need identical parts of those lines for the parallel lines. So what we do is we do morphological closing. We use a very long and thin horizontal structure which looks just like the nutrition fact line. We apply the morphological closing, and what it will do is it will fill in those broken lines, and it will give us solid lines which look almost identical. Yes, so this is it. This is exactly what we wanted. This is the exact line detected output where almost all the lines are seem so identical to each other because of the morphological filling, and we have also got rid of all those tiny letters at the end. So this is almost the perfect mask before just a few final steps. So as we saw in the last slide, the image that we got, it did not have more of the noises existing, but I have to make this algorithm as a very generalized one. So there can be some images where even after all these steps, there might be some noise still prevailing. So as a final step of noise removal, we apply the Otsu's method. Now what we do here is this basically adapts the image. It calculates a thresholding based on the clusters it detects in the image, and that threshold it uses to binarize the image again. So basically, all if there are any other small regions remaining in this image, it will get rid of those. Then whatever we have, we consider it as our golden mask, and we apply that mask. We multiply it with the original enhanced image that we had. We multiply with it, and all the small segments of the image that we get, we basically store them in an output folder. Let's see what the output we got after all these steps. This is it. This is exactly what we wanted. These are the segmented portions of the nutrition table. Each of these are individual events, so all the nutrition facts, just like these, are stored in an output folder where all of them are in a separate image, which can be passed by the further application, which we will explain in the next few slides. So what was the analysis of this whole project? So after testing this whole algorithm on 97 different nutrition fact labels taken from iPhone 5 or 5s cameras, the error rate calculated was 36%. So by error rate, what we mean is that uh, let's say after we will see that I will show the demo of this particular example that I've shown during the whole presentation. We will see that actual demo at the end of this video. But after taking this particular, after doing applying this algorithm on this particular image, we got two images. We which were the output of this algorithm, which were not really part of the nutrition fact. So that I consider the part of the error rate. And after applying those on 97 different images, there were images where not just two, more than 5 or 10 images that we got were really unwanted. So overall, the error rate was 36%. So 36% images that were output of this algorithm were really erroneous, and they were not the required information. But that means that there are 64% images which were really useful, which is a very good rate according to me. And we really faced a very big challenge during this. I faced a very big challenge during this project execution, which I will explain in the next slide, that what the challenge was. So if I got rid of that challenge, so there is room for improvement in this method, of course. So no, there is certainly room for improvement. So we will see what the challenge was. But if we discard that challenge, that ratio comes down to 34%. Challenges. So the biggest challenge we faced were barcodes. Why is barcode a bigger challenge? Is because as you understood the algorithm, it basically works on clustering all the horizontal lines that those are there in the nutrition fact. It preserves them and gets rid of all the portions. But when the nutrition fact picture also has barcode in it, what happens is barcode sometimes has more horizontal or vertical lines than the nutrition fact. In that case, when we do the clustering filter, the image considers the barcode as the bigger cluster, and it preserves that and gets rid of all the nutrition fact lines which we do not want. We will see one such example when we see the demo, but yes, the barcodes do create a lot of problems. Apart from that, alignment and lightning are big problems, which after the techniques that I actually already explained earlier, I have got rid of most of those problems. But yeah, there are certain characteristics when these problems still are there. So yes, the application. There are some really good applications with this algorithm, but one that comes to my mind is the one where we use this algorithm to detect the nutrition fact and help persons stay a healthy life. So what we do is we can develop an Android application on top of this algorithm. What it does is whenever a person goes to buy some grocery and stuff, and whenever he sees a new item and if he wants to eat it, he can take the picture of the nutrition fact. He can give it to this application. This application will apply this algorithm, segment out all the nutrition facts. It will pass it in text detection technique like OCR or something like that. That application, the data that has been detected by this application, it will give it to some preset data set, where according to the person's already given personal attributes like weight or body fat, blood sugar or something like that, the application will set and suggest the user that how much consumption of this particular food item is good for a person, given the nutrition facts on this table which the app already has. So this way, a person every time he wants to consume a new item can use this application, take the photograph of the nutrition fact, and he can know what is a good level of consumption for this particular person of this particular food item. Thank you, Professor Dapeng Oliver Wu. It was his motivation and guidance which made this project possible. This was done as a part of the coursework for class AAA 6512, which is Image Processing and Computer Vision at University of Florida in Gainesville. This is the paper based on which this whole algorithm was motivated. Alright, so this is the output directory of my image file, and here is the image that I have stored. Let's see the working. So this is the output directory in my images directory. Now this is the code that I am working on. As you can see in the code, I'll run it with the image that was there in the output directory. It loaded the image. It is preparing the environment for the processing. It now is oh, it started processing. It is doing everything: sensitivity, hoft, orientation, rotation, and as you can see, let's see what the output is. Oh, it detected the lines, and look at that. That's exactly what we wanted. All the no, all the segments of the image of this particular image, as you saw over here. We will go to this directory now and see how those are stored. So here as you see, it did one image, detected 18 lines. It took 22 seconds for that. In the output directory, under the same image name, you will see the folder, and these are all those 18 images. If I double click on it, okay, yeah, yeah. Here, so this is not this is what exactly what we wanted: saturation, fat, cholesterol, sodium, carbonated, and this is the output of the image. Uh, this is exactly what I wanted. So now I'm taking out that image, and just to show the robustness of this algorithm, I'm gonna go on Google, find a nutrition fact label online, and apply this algorithm on that. Let me find a suitable image. I want an image with some background. I think that okay, yeah, here this one is perfect. This one also has a lighting effect. As you can see here, there is a lot of light, so this area is, like less bright, in fact more bright compared to the other ones. So I'm gonna apply this algorithm on this particular image. Let's see how the output works. So this is the image, and you can see that it was a JPEG image, and here I've written JPEG. That's why it's detecting. If it was a PNG image, all I need to do is come here and change it to PNG instead of JPG. Now I am storing this image into the images directory of my output directory. I'm running it. It will load the new image, which it did, and now it's starting to. Okay, here it is. As you can see, it already detected the line. There are some of the lines are curved, and that's why we kept the eccentricity to 0.98 and not 1. And that's the reason it also detected those curved lines. Now I think here it's quite clear why we kept eccentricity as 0.98. And in the same image name, we have all these 13 images that we wanted. So because of this curvature, this was a little more than expected curvature. So this algorithm did not work exactly as it would, but see, as you can filtrate the images, it's just perfect as you wanted. How much saturated fat is there, trans fat is there. Uh, that's exactly the data you wanted. Now, as I discussed about those challenges in the image, let me go to Google and find an image with some barcodes. Oh, here it is. There's this image with some barcodes. Also, there are some lighting problems, lighting glares in the image. Let's see how this image works. As I discussed, because of these barcodes, this image might not work as really as expected. Because the barcodes, the cluster created by the barcodes is bigger than the cluster created by the nutrition facts. So the image will, the algorithm will rather detect barcodes than the nutrition facts. If it, let's see if it works exactly what I projected. So it's starting to enhance the image. Did enhance the image. Oh, as you can see, it got rid of all the nutrition fact lines and it only kept those barcode clusters. It kept these barcode clusters because those are the larger clusters than the image. And as you can see, the lines detected are not the nutrition facts, rather they are the horizontal lines uh, which are aligned to the barcodes. And these are all those lines that it detected, which is not really what we wanted. But as I said, there is certainly room for improvements, and if some way we can get rid of these barcodes, then this algorithm can be really, really good. All right, thank you so very much for your time. If you have any questions, please send it to me on ndnisarg@yahoo.com. Thank you so much.